Welcome back. This is Luke from Cadus Maths. We often see vectors and they can be represented on the 2D plane. But did you know that vectors can also be represented in the 3D space? In the 3D space, we have three perpendicular axes that meet at an origin. We have an x-axis, a y-axis, and a z-axis. And any point in the space can be described by a point we can label as P. Vectors in the 3D space have a magnitude and direction as well. This general formula can describe a vector in 3D space, given by its components x, y, and z, and three vectors I, j, and k. 3D space, represented by three perpendicular axes, is made up of vector I, which has length 1 in the x-axis, vector j, which has 1 unit in the y-axis, and vector k, which has 1 unit in the z-axis. Let's now look at an example where we have a vector described by 2i minus j plus 2k. You may have noticed that the numbers have replaced the letters x, y, and z. We see that 2i represents the I vector in 2 units in the x-axis, minus j, which is minus 1 unit in the y-axis, and 2k, which is 2 units in the z-axis. Let's join these vectors up tip to tail, form a point P, and from the origin we can now form a vector which points to this direction 2i minus j plus 2k. Did you know that vectors have a very unique property which allow it to either decrease or increase in size but in the same direction, or even decrease or increase in size in the opposite direction? We are now going to explore the unique properties of scalars that rely on one single number, and that is the magnitude. Let's do an example where we have vector a to b, which is equal to 2i minus j plus 2k. Let's say we wanted to double the length of vector AB, we would write 2AB. If we wanted to halve the vector AB, we would write 0.5 in front of it. And instead, if we wanted to say double the vector length but in the opposite direction, we would write minus 2AB. Let's see what it looks like algebraically. We put the minus 2 and we multiply it by the entire vector. And if we expand this bracket, we get minus 4i plus 2j minus 4k. If we have a vector starting from the origin and extending to some point A, where the vectors are I plus j plus k, and we wish to multiply it by a scalar of -2, we should have a new vector that's double in magnitude but opposite in direction. We will call this new vector -2 OA. This arrow represents vector OA and has the equation I plus j plus k. If we scale it by a factor of -2, it's going to be doubled in magnitude but opposite in direction as seen here. Let's return to our vector OA, but this time let's now multiply it by a scalar of 0.5. What this means is each component is multiplied by 0.5, so it should be half the length of its original size. Let's now have a look. Our orange arrow represents the vector OA. If we multiply it by a scalar of 0.5 or half, our vector arrow is now half the length but in the same direction. Finally, if we now want to scale our vector OA by a factor of 2, each component in OA should now be doubled, 2i plus 2j plus 2k. What this means geometrically is that our vector arrow should be double in its length but still point in the same direction. Let's see our vector OA. If we scale it by a factor of 2, it is now double its length, but still points in the same direction. Scalars are a quantity with only a magnitude. Throughout this video, we have used numbers to represent scalars, but in general, let's use lambda to represent any scalar value. From this video, we have seen and observed that scalars can either make a vector increase in the same direction or decrease in the opposite direction, depending on the value of the scalar. Thanks so much for watching, and once again, I'll see you in the next one.